Hello everyone. Today we are going to solve a 2D transient heat conduction problem in cylindrical coordinates using FTCS or forward time centered space finite difference method. Our objectives are to present a simple 2D heat conduction problem in cylindrical coordinates. The temperature variation is along the radial direction and along the phase angle phi. We'll solve the problem using FTCS finite difference method. We'll vary grid spacings and obtain solutions using FDM and present the results graphically. The domain is shown here. It is basically a heart-shaped figure. So inside the domain, inside that heart-shaped figure, the initial temperature is maintained at say 1000 degrees Celsius. The boundary temperatures along the blue colored lines are maintained at 0 degrees Celsius. And we're going to find out the temperature distribution with time. The general heat conduction equation in 3D cylindrical coordinates is given as dou square T over dou R square plus 1 over R times dou T over dou R plus 1 over R square times dou square T over dou phi square plus dou square T over dou Z square plus G over K equals 1 over alpha times dou T over dou T. Here the uppercase T is a function of R5Z and lowercase t. R represents the radial dimension, phi the phase angle, Z the vertical dimension, and T in time represents the time in seconds. Alpha is the material property called thermal diffusivity and is given in meters squared per second, and alpha equals K over rho C, where K is the thermal conductivity of the material in watts per meter Kelvin, rho is the density of the material in kilograms per meter cube, and C is the specific heat capacity of the material in joules per kilogram Kelvin. And G represents the volumetric rate of internal heat generation in watts per meter cube. Here we assume that the thermal conductivity K is uniform in the domain. In other words, it's homogeneous and isotropic. Our interest is to do a 2D problem. So for a 2D transient heat conduction along radial direction and along the phase angle with no heat generation, we'll simplify equation 1 as follows. Here we assume that the temperature does not vary significantly in z direction when compared with the radial direction. Example, top and bottom surfaces are insulated, and the phase angle as well. So there is no heat generation, so G equals 0. Accordingly, we get dou square T over dou R square plus 1 over R times dou T over dou R plus 1 over R square times dou square T by dou phi square equals 1 over alpha times dou T over dou T, and T is a function of R, phi and T. The initial condition is given as T at R comma phi comma T equals 0 equals T in, which is equal to say 1000 degrees Celsius at the interior nodes. At the boundary nodes where R is greater than equal to R limit, we're going to establish R limit a little later. When R is greater than R limit, T at R comma phi comma T equals T boundary, which is equal to say 0 degrees Celsius at time T is greater than or equal to 0. Our interest is to obtain the temperature distribution T at R comma phi comma T, and to obtain T R comma phi comma T, we need to solve the above PDE. We will utilize finite difference method to solve the above PDE. To do so, we need to replace the partial derivatives with finite difference approximations. we'll replace both the space derivatives r comma phi with center difference approximations and the time derivative with first order forward difference approximation. Let I represents the node location along the radial direction and j represents the node location along the phase angle. Then our finite difference equation is written as ti minus 1 comma j at n minus t minus 2 times ti comma jn plus ti plus 1 comma jn over delta r square plus 1 over ri times ti plus 1 comma jn minus ti minus 1 comma jn over 2 delta r plus 1 over ri square times ti comma j minus 1 n minus 2 times ti comma jn plus ti comma j plus 1 n over delta phi square equals 1 over alpha times ti comma jn plus 1 minus ti comma jn over delta t. We will rearrange this equation as shown below. And we'll rearrange the equation further as shown in the screen. And we let d equals alpha times delta t over delta r square. Accordingly, we get equation 3, which is shown as ti comma jn plus 1 equals ti comma jn plus d times ti minus 1 comma jn minus 2 times ti comma jn plus ti plus 1 comma jn plus delta r over 2ri times ti plus 1 comma jn minus ti minus 1 comma jn plus 1 over ri square times delta r square over delta phi square times ti comma j minus 1 n minus 2 times ti comma jn plus ti comma j plus 1 n. Here d represents an analogous diffusion number that is typically used in Cartesian coordinates. So equation 3 is the finite difference approximation of the original partial differential equation PDE we are trying to solve. As mentioned before, I and j represents the node location on the discretized domain, and the finite difference tensor is given below. So now let's look at the boundary conditions. There are a number of equations available to represent the geometry of a heart. I am using one particular heart equation that is given in polar coordinates. I'm just calling it r underscore limit at 5 equals 2 minus 2 times sine of phi plus sine of phi times square root of absolute of cos phi over sine of phi plus 1.4. This represents the boundary of the heart or the heart geometry as shown in the red colored lines curved apart. So our boundary conditions are as below. If r is greater than or equal to r limit for any phi, tr comma phi equals tb. At the center portion, r equals 0, we consider that dou t over dou r equals 0, and accordingly, when we use forward difference approximation, ti plus 1 comma jn minus ti comma jn over delta r equals 0 for I equals 0 for all j. So accordingly, we get t0 comma j equals t1 comma j for all j. This is the boundary conditions. Inside the heart geometry, we use equation 3. That is, if r is lesser than r underscore limit for all 5. Tr of 5 is equal to ti comma jn plus 1, which we have derived earlier and is given below. So this stability criteria is a little bit involved, and we will use von Neumann method. According to von Neumann method, if we have fi plus slash minus n, we represent this as fi at n times e plus slash minus I times km star delta x. Here km is the wave number, which is equal to 2 pi m by 2l, and here m varies from 1 to infinity and I equals square root of minus 1. So if we represent theta as km times delta x, we get fi plus or minus 1 at n equals fin times e plus or minus I times theta. And we can compare this to an equation fin plus 1 equals g times fin. Here the amplification factor is g, and the condition we need to meet for stability is the modulus of g should be lesser than or equal to 1. Here we need to use the identity cos theta equals e per I theta plus e per minus I theta by 2, and sin theta equals e per I theta minus e per minus I theta over 2i. So we have rewritten equation 3 here, and we are replacing ti minus 1 comma jn, for example, with the previous relationship we obtained. So for example, ti minus 1 comma jn n equals ti comma jn times e per minus I times km times delta r. So likewise we replace other variables such as ti plus 1 comma jn, ti comma j minus 1 n, and ti comma j plus 1 n in terms of e power minus I theta and tijn, which is shown on the next line. Let's call theta 1 equals km times delta r and theta 2 equals km times delta phi, and then we substitute the values on the line below, and we rearrange this equation and we replace these exponential terms in terms of cosines and sine thetas, and we get this equation. So from which, when we compare this to the other equation, that is fin plus 1 equals g times fin, we can obtain the amplification factor g from the previous equation. Accordingly, g is taken and shown here, and we need to meet our stability criteria. Absolute value of g should be lesser than or equal to 1. So here cos theta 1 can vary from minus 1 to positive 1, and likewise cos theta 2 can vary from minus 1 to positive 1, and sin theta 1 can vary from minus 1 to positive 1. Accordingly, we get a number of different cases, and we need to make sure that we meet all those cases for stability. So some of the cases are given here. Case 2, for example, I call it G2, which is equal to square root of 1 minus 4 times D whole square. And case 3 is given here. And case 4 is given here. Case 5, case 6, case 7, and case 8 here we have G8, which is equal to G7. Likewise, we earlier for case 4, G4 equals G3. We can then solve for a typical example. Let alpha equals 1 e to the negative 4 meter square per second, and delta t equals 1 over 6 seconds, delta r equals 0.39 meters, and delta phi equals pi over 5. Then we get d value, which is equal to alpha times delta t over delta r square, which is equal to 0.000109577. We need to verify the stability condition using Born-Newman stability condition requirement. As an example, let at time t equals 0, the boundary temperature Tb equals 0 degrees Celsius. For all t greater than equal to 0, that is n is greater than or equal to 0, the initial temperature inside the domain T equals Ti, J0 equals 1000 degrees Celsius. Let n equals 0 and R10 equals 2 meters. So at the 10th step, based on the Hart equation, we get a radius value of 2 meters. And our equation 3, which we derived earlier, is given below. And we need to substitute the values of all these initial and boundary conditions and the d value into the previous equation. And we get, for the first time step, we get a value of 999.86. Let's go back to MATLAB now. So this takes a little bit time to run, so it's been running in the background. The alpha value is given as 1e to the negative 4, and kT equals 386 watts per meter Kelvin appropriate units. Rn equals 0.1 meter. The radius, the maximum radius is 4 meters. The inside radius, or the smallest value, is 0.1 meter here. And we divide the radial dimension into 100 sections. Accordingly, m equals 100. Delta r is each segment length is r out minus r in over m. And total number of radial points is nr equals m plus 1. And let's consider a number of steps along the face angle as 100. So delta phi, the angle step, is 2 times pi over n phi. And let's consider total time t as 5000 seconds. And the number of time steps as 30,000. And each time step delta O underscore t equals t over nt. The boundary condition is given as 0 degree Celsius, and the initial temperature inside the domain is given as 1000 degrees Celsius. We'll look at the graphical part. So as I mentioned here, this has been running for some time. The initial temperature profile is given on the top left hand side at time t equals 0 seconds, and the final temperature profile at time is equals 5000 seconds is shown on the bottom left hand side. On the right hand side we see the animation. For example, at time equals 530 odd seconds. This is going to run till we hit 5000 seconds. So we'll close this screen and we'll run a simpler case to verify our values we obtained previously. Let's change the number of sections m to 10 and the number of angle steps to 10, and we'll keep this CS 3 and say 18. We have delta t equals 1 over 6, and we'll save this and rerun this case. So we have to make sure we meet the stability criteria in this case. We have this d value and the various von Neumann stability limits are given as G2, G3, G5, G6 and G7. They're all lesser than 1, so the condition is stable here. And at the boundary we have this value just inside the boundary, 999.86, which we calculated over here, 999.86 at 10 comma, it should be 10 comma 1 node. For the first time step. So our answers match here, 999.86. So we can close this screen. We can maybe increase this, go back, and then we'll say 3000 seconds and 18,000. In this case, the time step, the delta t needs to be small. We'll go to the PowerPoint in the meantime, and so we obtained basically for one single temperature value, one single point, we found the temperature at the first time step as 999.86. So we follow the same procedure and obtain temperatures for the other nodes in the domain as well, and we then find the temperature distribution in the domain for the next time step and so on. So we presented graphical results in MATLAB, so we can do a general purpose develop codes by varying the grid spacings and time steps. and we can obtain more refined solutions. To summarize, we presented a 2D transient heat conduction problem in cylindrical coordinates. The temperature variation is along the radial direction as well as along the phase angle. We follow here for the boundary the geometry of the heart as we uh, got from a heart equation. We solved the problem using FTCS finite difference method and we obtained the temperature profile. We resolved the problem using smaller grid spacings and presented the results. In future videos, we can explore more challenging problems. If you have any comments or questions, please post it. Thanks for watching. Now we can go back to MATLAB and see how it's doing. For the second time we were running it. So it's now at is going to run for 3000 seconds. And now it's at 15.8 or 16 seconds closed. Thanks everyone for watching again.